Hello, sixth graders. Today we're multiplying by the powers of 10. I'm going to teach you a couple tricks here so it's not real confusing, but you have to be pretty neat with your work today because you're moving the decimals often. Because when you're working with decimals, everything is by tens with place value. Pretty simple stuff here. So this nice little chart here at the top, I'm going to kind of make sense of this chart. It's called sum powers of 10. Right here we've got the decimal, okay? So to the powers of 10, we're at an exponent. So we're going to work to the left of the decimal right now. And you see this 10 to the 0 power, that equals 1. 10 to the 1 power, that'd be like 10. 10 to the second power would be 10 times 10, which would equal 100. 10 to the third power is the same as saying 10 times 10 times 10, which equals 1,000. Take a look at how many zeros are here, 1,000. 10 to the fourth power, so 10 to the exponent 4, is just like saying 10 times 10 times 10 times 10 is 10,000. Most common error that kids see that I've been teaching over all my years is 10 to the fourth power, kids just want to put 40 right away. This doesn't mean 10 times 4. This means 10 times 10 times 10 times 10, 4 times, okay? 1 will always be the answer and 0 will be in there. You can do this. Now, today is a little new because we're working to the right. So now we're to the negative exponent. So if you see 10 to the negative 1, that is the same as saying 1/10 or 0.1. 10 to the negative 2 is the same as saying 1/10 times 1/10, which is the same as 0.01. 10 to the negative 3 is 1/10 times 1/10 times 1/10, which is the same as saying 0.001. 10 to the negative 4. 1, 2, 3, 4. You get it. 4 numbers after the decimal. So we see this problem right here. You're like, whoa, do I have to do long multiplication with this? Absolutely not. If I see kids doing long multiplication with this, that means you didn't watch my video, you're not listening to my tricks, and you are making math much harder than it has to be. This is the technique that I want you to realize, okay? When you see this number right here, 4.9 times 0.001, you have to think this. How many numbers are after the 0? Or how many after the decimal, I apologize. We have 1, 2, 3. So I'm going to write this a little bigger so you can kind of see it. We have 3 numbers after the decimal here. We're looking at the number 0.001. I'm going to move this, so I'm going to count here. I'm going to count 1, 2, 3. There's 3 numbers after the decimal. So when you look at 4.9 here, I have to move my decimal because it's here. I have to move it to the left and make this smaller. Moving it 1, 2, 3. Here's my decimal here. So to fill in the numbers here. So my answer is 0.0049. Once again, this first 0 before the decimal doesn't really matter. 0.0049. So all I did was I took a look at this number here, counted how many numbers are after the decimal, and then I moved this decimal to my left. As many times. I'm going to do another one just for an example here. Okay. 7.8 times 0.01. So look closely. I'm going to write 0.01 a little bigger. How many numbers are after the decimal? 2. 1, 2. So when I look at 7.8, I have to move this decimal to the left 2 places. 1, 2. My 0 goes there because the decimal could be here. Now the decimal's here. 1, 2. So my answer is 0.078. Now this one looks really confusing. 30 times 10 to the negative 1. I don't remember what 10 to the negative 1 is, so I'm going to look at my chart. It's the same as saying 0.1. So I'm going to rewrite this problem so it makes sense so I'm not confused. 0.0, oops, 0.1, 0.1, okay? So I'm going to ask you this question. By the way, the number 30, the decimal's right there. It's a hidden decimal, right? Move this decimal 1 spot. So this decimal right here moves 1 spot. So your answer is 3. I'll show you again. 30, the decimal's here, times 0.1. I move the decimal here 1 space. So I'm going to move this decimal 1 space right there. So my answer is 3. Or 3.0, whatever you want, but it's the same thing. 7 times 10 to the negative 2. What does 10 to the negative 2 mean? 0.01. So 7 times 0.01. So let me ask myself, how many numbers are after the decimal? 1, 2. The number 7, the decimal's here, right? I have to move it 2 decimals. 1, 2. Decimals here now. This is a 0. My answer is 0.07. I want you in the habit of putting that 0 there to the left, but 0.07 is my answer. Take a look at this one. This is 0.15 times 10 to the third power. It's not a negative number. The exponent's a positive number, so I'm looking here. 10 to the third power is 1,000. So let's watch closely here. We have to the thousands, that means we get to move this decimal to the right 3 times, which is pretty awesome. So watch here. 0.15. If it's a positive 3, I get to move this decimal 3 spaces to the right. 1, 2, 3. So my answer is 150. Do you see how I did that, kids? It's no longer negative. It's a positive 1. So then I can just move my decimal for however many that exponent says. 1.9 times 100. Let's take 100 is right here. This is 10 to the second power. It means the same thing, right? So if at 1.9, and it's a positive number, I get to move this decimal 2 spaces to the right and make a bigger number. 1, 2. So my answer is 190. The number is a positive. It's a 2. So 37.6 times 10 to the second power. I'm going to move this decimal 2 spots. 1, 2. So my answer is 3,760. Back to the negative numbers. 10 to the negative 3. Let's take a look here. Negative 3 is the same as saying 0.001. Okay. I have 42.8 times 10 to the negative 3 or times 0.001. How many numbers are after the decimal in 0.001? 1, 2, 3. There's 3 numbers. So that means I'm going to be moving this. It's negative, so I can't make it bigger. I can't go this way. I have to go to the left. So it's 1, 2, 3. So my answer is 0.428. Okay. Take a look at this problem. A mathematician, Edward Kaisner, asked his 9-year-old nephew to invent a name for the number represented by 10 to the 100th power. The boy named it Google. Later in the event, an even larger number was named Googleplex. This number is represented by 10 to Google, or 10 to the 10 to the 100. Holy moly. How many zeros are in the standard form of Google or 10 to the 100? How many zeros? There are 100 zeros, right? Because the zeros there. One Googleplex is followed by how many zeros? 10 to the 100. I'm not asking you to have this memorized or anything. That's just kind of an interesting problem. This next one. The speed of a computer memory and logic chips is measured in nanoseconds. A nanosecond is 1/1000th of a second, or 10 to the 9th second. Write this number in standard form. Got a decimal? This is a 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 places. It said 1/1000th, so put a 1 here. Put all these zeros in here. See how I did that? All I did is look at this -9, counted 9 spaces to the right of my decimal because that would be my negatives. My positives would be on my left, and there's my answer. This next problem's kind of a fun one. Light travels at about 1 million in this many seconds. 0.00005 seconds. If a spacecraft could travel at this speed, it would travel at almost 10.6, or not 10.6, 10 to the 6th power miles in 5 seconds. Okay. How many would travel in 50 seconds? You're probably like, I have no idea how to do this. Watch closely. 10 to the 6th power is this. 1, 2, 3, 4, 5, 6, right? It's 1 million. So all I'm doing is taking 1 million and I'm multiplying it by 10, because 5 times 10 equals 50. So what's 1 million times 10? Well, just add another 0. One, two, three, 4, 5, 6, 7. The answer is 10 million, which would be 10 to the 7th power. That's how easy it is. I like this next one. Mentally calculate your change from $10. Probably wondering, how do I do this? Watch closely. If $10 is our total for each one of these, 475, what is that closest to? It's closest to $5. How close is 475 to $5? All of you are pretty good with money because everyone likes money. Because when you have money, you can buy candy and pop and toys and just all sorts of awesome things. 475 is 25 cents. It takes 25 cents to get to $5. And how close is $5 to $10? It's $5. The answer is $5.25 and change. Something costs 89 cents. Well, how close is 89 to a dollar? It's 11 cents away from a dollar. How close is $1 to $10? It's $9 away. So your change would be $9.11. Let's go over here. $3.98. How close is that to $4? It's 2 cents off. Okay. How close is $4 to $10? It's $6 away. This would be 0.2. If you put it at, or 0.02, if you put it at 0.2, that would be 20 cents. So $6.02. How about this one? Ooh, this one gets a little more challenging. I like it. $8.46, as close as we can to $10. What would be my change? Well, we're going to take this and get as close to $8.50 as possible, right? Which would be 4 cents. Follow along with me, okay? If I'm at $8.50, I need 4 cents to get there, and then $8.50 to $9 would be another 50 cents. And once we're at $9 to $10, that would be one whole dollar. If I add all these up, I've got $1.54. That's how my brain works. Hopefully your brain works the same way. Today's math lesson was interesting. It dealt with the smaller numbers with the negative exponents. Hopefully this helped. Make sure to, if anything, if it's like 10 to the negative exponent, remember you can always change it into decimal form and it'll make a little sense, and then you can move that decimal along. Remember to ask questions. If any part of this video didn't make sense, please bring those questions to math and I will help you, of course. Good luck with math today.